Hi, let's start with the most interesting chapter of grade 10 circles. Many students have a fear for this chapter, but I promise you, if you pay good attention, this can be the most scoring chapter of grade 10. So, before we begin, let's quickly go through some facts. First, what is a circle? Well, it is a collection of all points in a plane which are at a constant distance that we call the radius from a fixed point called the center of the circle. Now, let's know a few more terms like secant, which is the line that touches the circle at exactly 2 points. Next is tangent of a circle. It is the line that touches the circle at exactly 1 point. The word tangent comes from the Latin word tangere, which means to touch. The common point of the tangent and the circle is called the point of contact, and the tangent is said to touch the circle at the common point. The line containing the radius through the point of contact is also called the normal to the circle at that point. Also, there is only one tangent at a point of the circle. We can say that tangent of a circle is a special case of the secant when the two endpoints of its corresponding chords coincide. Now let's see some properties of the tangent. Tangent at any point of a circle is perpendicular to the radius through the point of contact. So we are given a circle with center O and a tangent xy to the circle at a point P. We need to prove that OP is perpendicular to XY. Let's do a construction first. Take a point Q on XY other than P and join OQ. First, please understand that the point Q must lie outside the circle. Why? That is because if Q lies inside the circle, XY will become a secant and not a tangent to the circle as given. Therefore, OQ is longer than the radius OP of the circle, that is, OQ is greater than OP. Since this happens for every point on the line XY except the point P, OP is the shortest of all the distances of the point O to the points of XY. So, OP is perpendicular to XY because perpendicular is the shortest distance between 2 points. From this theorem, we can also conclude that at any point on the circle, there can be one and only one tangent. Let's see exercise 10.1 now. Hope you are good to start the exercise now. Exercise 10.1, question 1. How many tangents can a circle have? The answer is there can be infinite tangents to a circle. A circle is made up of infinite points which are at an equal distance from a point. Since there are infinite points on the circumference of a circle, infinite tangents can be drawn from them. Let's see question 2. Fill in the blanks. A tangent to a circle intersects it in how many points? Exactly 1 point. A line intersecting a circle in 2 points is called a secant. A circle can have dash parallel tangents at the most. Answer is 2. The common point of a tangent to a circle and the circle is called the point of contact. Okay, let's see question 3. A tangent PQ at a point P of a circle of radius 5 cm meets a line through the center O at a point Q so that OQ is equal to 12 cm. You have to find out what length of PQ is. Now, Since a line drawn from the center of the given circle to a tangent is perpendicular to it, OP is perpendicular to PQ. Now, using Pythagoras theorem, OQ square is equal to OP square plus PQ square. That means 12 square is equal to 5 square plus PQ square, which gives us PQ square is equal to 119, and thus PQ is equal to square root of 119. Question 4. Draw a circle and two lines parallel to a given line such that one is a tangent and the other a secant to the circle. Let's first understand what is secant. Well, it is a line that touches the circle at exactly 2 points, whereas tangent of a circle is the line that touches the circle at exactly 1 point. Now, here XY and AB are two parallel lines. Line segment AB is the tangent at point C, while line segment XY is the secant. Now let's understand a few more concepts before moving on to the next exercise. First is length of a tangent. The length of the segment of the tangent from an external point P and the point of contact with the circle is called the length of the tangent from the point P to the circle. For example, here both PQ and PR are the length of tangent from an external point P. Now let's see a theorem based on the length of a tangent. It says the lengths of the tangents drawn from an external point to a circle are equal. Let's see the proof now. We are given a circle with center O and two tangents PQ, PR on the circle from an external point P. We need to prove that PQ is equal to PR. First, join OP, and if not done already, join OQ and OR too. Let's see the proof now. Now OR is perpendicular to RP because tangent at any point of a circle is perpendicular to the radius through the point of contact. Similarly, OQ is perpendicular to PQ. Now in triangles OPQ and OPR, OQ is equal to OR because these are the radii of the same circle. Angle ORP is equal to angle OQP, and both are equal to 90 degrees, and OP is common. Therefore, by RHS congruency, triangle OPQ is congruent to triangle OPR. Thus, PQ is equal to PR. To understand the concepts better, let's go through a few examples. The first is we are given two concentric circles C1 and C2. There's a center of these circles which is O, and a chord AB of the larger circle C1 touches the smaller circle C2 at the point P. We need to prove that AP is equal to BP. Let us join OP. Then AB is a tangent to C2 at P and OP is its radius. Therefore, by theorem 10.1, OP is perpendicular to AB. Now AB is a chord of the circle C1 and OP is perpendicular to AB. Therefore, OP is the bisector of chord AB because the perpendicular from the center bisects the chord. That is, AP is equal to BP. Let's see one more example now. Two tangents TP and TQ are drawn to a circle with center O from an external point T. We need to prove that angle PTQ is equal to twice of angle OPQ. Let angle PTQ be theta. Now, TP is equal to TQ because the lengths of tangents drawn from an external point to a circle are equal. Triangle TPQ is an isosceles triangle. Now angle TPQ would be equal to angle TQP because angles opposite to equal sides of a triangle are equal. Now theta plus angle TPQ plus angle TQP would be 180 degree, angle sum property of a triangle. Or we can say theta plus twice of angle TPQ is equal to 180 degrees. That means TPQ is equal to 90 degree minus theta by 2. Now angle OPT is equal to 90 degrees. Angle OPQ is equal to angle OPT minus angle TPQ. Substituting the given values, we get angle OPQ equal to theta by 2, or we can say theta is equal to twice of angle OPQ. Question 1. From a point Q, the length of the tangent to a circle is 24 centimeter and the distance of Q from the center is 25 centimeter. The radius of the circle is. Now OP is perpendicular to PQ because the tangent at any point of a circle is perpendicular to the radius through the point of contact. Therefore, OQ square is equal to OP square plus PQ square, Pythagoras theorem. This means 25 square is equal to OP square plus 24 square, which means OP square is equal to 25 square minus 24 square. Thus, OP square is 625 minus 576. Or we can say OP square is equal to 49 and thus OP is equal to 7 centimeter. Question 2. TP and TQ are the two tangents to a circle with center O such that angle POQ is 110 degrees. We have to find angle PTQ. OP is perpendicular to PT and TQ is perpendicular to OQ. Why? Because the tangent at any point of a circle is perpendicular to the radius through the point of contact, right? Also, angle PTQ plus angle POQ plus angle OPT plus angle OQT would be 360 degree because sum of angles of a quadrilateral is 360 degrees and OPTQ is a quadrilateral here. Substituting the given values, we get angle PTQ is equal to 70 degrees. Question 3. Tangents PA and PB from a point P to a circle with center O are inclined to each other at an angle of 80 degree. Find angle POA. OA is perpendicular to PA and OB is perpendicular to PB, which means angle OBP is equal to angle OAP equal to 90 degree. Because tangent at any point of a circle is perpendicular to the radius through the point of contact. Now angle AOB plus angle OAP plus angle OBP plus angle APB is equal to 360 degree because sum of angles of a quadrilateral is 360 degrees. That means angle AOB plus 90 degree plus 90 degree plus 80 degree is 360 degree. That means angle AOB is equal to 100 degrees. Now in triangle OPB and triangle OPA, AP is equal to BP. These are the lengths of tangents drawn from an external point. OA is equal to OB. These are the radii of the same circle. And OP is common. Therefore, by SSS congruency rule, triangle OPB is congruent to triangle OPA. So, angle POB is equal to angle POA by CPCT. That means angle POA is equal to 100 by 2, that is 50 degree, which is also equal to angle POB. Question 4. Prove that the tangents drawn at the ends of the diameter of a circle are parallel. Here AB is the diameter of the given circle, PQ and RS are the two tangents, OA is the radius to the tangent PQ, and OB is the radius to tangent RS. Now OA is perpendicular to PA and OB is perpendicular to PB. Because the tangent at any point of a circle is perpendicular to the radius through the point of contact. That means angle OAP is equal to angle OAQ, also equal to angle OBR and angle OBS. And all of these are equal to 90 degree each. Now angle OBR and angle OAQ, these are alternate interior angles. Similarly, angle OBS and angle OAP are alternate interior angles. Since alternate interior angles are equal, PQ is parallel to RS. Question 5. Prove that the perpendicular at the point of contact to the tangent of a circle passes through the center. Let O be the center of the given circle. A tangent PR has been drawn touching the circle at point P. Draw QP perpendicular to RP at point P such that point Q lies on the circle. Now angle OPR is equal to 90 degree because radius is perpendicular to the tangent. Also, angle QPR is equal to 90 degree. It is given. Therefore, angle OPR is equal to angle QPR. Now, this is possible only when center O lies on the line QP. Hence, perpendicular at the point of contact to the tangent to a circle passes through the center of the circle. Question 6. The length of a tangent from a point A at a distance 5 cm from the center of the circle is 4 cm. Find the radius of the circle. OB is perpendicular to AB because the tangent at any point of a circle is perpendicular to the radius through the point of contact. In triangle ABO, OA square would be equal to AB square plus BO square by Pythagoras theorem. That means 5 square is equal to 4 square plus BO square, or we can say BO square is equal to 9, and thus BO, that is the radius of the circle, is 3 centimeter. Question 7. It says two concentric circles are of radii 5 centimeter and 3 centimeter. We need to find the length of the chord of the larger circle which touches the smaller circle. So here AB is the chord of the larger circle which touches the smaller circle at the point P. Now this AB is tangent to the smaller circle because it is touching the smaller circle at only one point, which means OP is perpendicular to AB because the tangent at any point of a circle is perpendicular to the radius through the point of contact. Now using Pythagoras theorem in triangle AOP, OA square is equal to AP square plus OP square. First we would find out AP, which gives us this. Upon solving this, we get AP is equal to 4 centimeter. Now, perpendicular from the center of the circle bisects the chord. This is one theorem. That means AP is equal to PB. Thus, AP is equal to 4 and PB is equal to 4. So, AB, which is AP plus PB, it will be equal to 8 centimeter. And this is the chord that we need to find the length for. So, the length of the chord of the larger circle is 8 centimeter. Question 8. A quadrilateral ABCD is drawn to circumscribe a circle. Prove that AB plus CD is equal to AD plus BC. We know that the length of tangents from an external point are equal. Hence, dr is equal to ds. These are tangents from an external point D. Cr is equal to cq from an external point C. AP is equal to AS, tangents from an external point A, and BP is equal to BQ because these are tangents from an external point B. Adding these equations, we get, rearranging, we get this, and hence AB plus CD is equal to AD plus BC, which is what we wanted to prove. Question 9. XY and X dash Y dash are two parallel tangents to a circle with center O and another tangent AB with point of C intersecting XY at A and X dash Y dash at B. Prove that angle AOB is equal to 90 degree. In triangle OPA and triangle OCA, OP is equal to OC because both are the radii of the same circle. AP is equal to AC. These are tangents from an external point A. OA is common. Therefore, triangle OPA is congruent to triangle OCA via SSS congruency. Similarly, triangle OQB is congruent to triangle OCB. That means angle POA is equal to angle COA, CPCT, and angle QOB is equal to angle COB, CPCT again. Since the line POQ is a straight line, it can be considered as a diameter of the circle. Therefore, angle POA plus angle COA plus angle COB plus angle QOB, their sum is 180 degree. They all lie on the straight line. Now from these equations we get twice of angle COA plus twice of angle COB is equal to 180 degree because angle POA is equal to angle COA and angle QOB is equal to angle COB, which further implies that angle COA plus angle COB is equal to 90 degree, or we can say angle AOB is equal to 90 degrees. Question 10. Prove that the angle between two tangents drawn from an external point to a circle is supplementary to the angle subtended by the line segment joining the points of contact at the center. First, draw a circle with center O. Choose an external point P and draw two tangents PA and PB at points A and B respectively. Now, join A and B to make AB in a way that it subtends angle AOB at the center of the circle. Now, angle OAP is equal to 90 degree because it is the radii to the tangent. In a similar way, the line segment OB is perpendicular to PB. So angle OBP is 90 degree and angle OAP is 90 degree. Now, in the quadrilateral OAPB, sum of all angles of the quadrilateral is 360 degree. Substituting the values, we get angle APB plus 90 degree, which is the value of angle OAP, plus 90 degree, which is the value of angle OBP, plus angle BOA is 360 degree. So, angle APB plus angle BOA is equal to 180 degree. That is, the angle between the two tangents drawn from an external point to a circle is supplementary to the angle subtended by the line segment joining the points of contact at the center. Question 11. Prove that the parallelogram circumscribing a circle is a rhombus. Now consider a parallelogram ABCD which is circumscribing a circle with a center O. Now since ABCD is a parallelogram, it is given, therefore AB is equal to CD and BC is equal to AD because opposite sides of a parallelogram are equal. Now, dr is equal to ds, bp is equal to bq, cr is equal to cq, and ap is equal to as. Why? Because lengths of tangents from a common point to the circle is equal. Adding all these, we get this. Now let's rearrange it. We would get this. Therefore, we get AB plus CD is equal to BC plus AD, which gives us, now AB is equal to CD and BC is equal to AD. It is given because it is a parallelogram. Therefore, we can say that twice of AB is equal to twice of BC, which means AB is equal to BC. Now, since AB is equal to BC, AB is also equal to CD, and BC is also equal to AD, we can say that AB is equal to BC, which is equal to CD and also equal to DA. So all the four sides are equal. Therefore, ABCD is a rhombus. Question 12. A triangle ABC is drawn to circumscribe a circle of radius 4 cm such that the segments BD and DC, into which BC is divided by the point of contact D, are of lengths 8 cm and 6 cm respectively. Find the sides AB and AC. Now CF is equal to CD, which is equal to 6 cm, because lengths of tangents from an external point to the circle are equal. Similarly, BE is equal to BD, which is equal to 8 centimeter. Let's suppose AE is x centimeter, so AF would also be x centimeter. Now AB would be 8 plus x, CA would be 6 plus x, and BC would be equal to 6 plus 8. The semi-perimeter of a triangle is given by the formula 2s, where s is the semi-perimeter, is equal to sum of the lengths of the sides of the triangle. So, substituting the values, we get semi-perimeter as 14 plus x. Now, area of a triangle is square root of s into s minus a into s minus b into s minus c, where s is the semi-perimeter and a, b, c are the lengths of the sides of the triangle. Substituting the given values, we get this, which upon solving gives us square root of 14 plus x into 48x. Now, area of triangle ABC would also be area of triangle AOF plus triangle FOC plus triangle COD plus triangle DOB plus triangle BOE plus triangle EOA. Now, area is also given by half into base into height. So, area of triangle AOF would be half into x into 4. Area of triangle FOC would be half into 6 into 4. Area of triangle COD would be half into 6 into 4 again. Area of triangle DOB would be half into 8 into 4. Area of triangle BOE would be half into 8 into 4 again. And area of triangle EOA would be half into x into 4, which gives us area as 56 plus 4x. From these two equations, we get square root of 14 plus x into 48x is equal to 56 plus 4x. Squaring both the sides, we get thus we get the value of x as 7 centimeter. That means AB is equal to 8 plus 7, that is 15 centimeter, and AC is equal to 6 plus 7, that is 13 centimeter. Question 13. Prove that opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the center of the circle. In triangle OAP and triangle OAS, AP is equal to AS. These are tangents from the same point A. OA is common. OP is equal to OS as these are the radii of the same circle. So, by SSS congruency, triangle OAP is congruent to triangle OAS. Hence, angle POA is equal to angle AOS by CPCT. Let's call them angle 7 and angle 8. In the same way, angle 1 is equal to angle 2, angle 3 is equal to angle 4, and angle 5 is equal to angle 6. We know that sum of all these angles is 360 degrees. Rearranging gives us, that means twice of angle 2 plus angle 3 plus twice of angle 6 plus angle 7 is equal to 360 degrees. That means angle 2 plus angle 3 plus angle 6 plus angle 7 is equal to 180 degrees. Or we can say angle COD plus angle AOB is equal to 180 degrees. Similarly, it can be proved that angle BOC plus angle DOA is also equal to 180 degree. Therefore, the opposite sides of any quadrilateral which circumscribes a given circle will subtend supplementary angles at the center of the circle. Thank you. Question 13. Prove that opposite sides of a quadrilateral circumscribing a circle subtend supplementary angles at the center of the circle. In triangle OAP and triangle OAS, AP is equal to AS. These are tangents from the same point A. OA is common. OP is equal to OS as these are the radii of the same circle. So, by SSS congruency, triangle OAP is congruent to triangle OAS. Hence, angle POA is equal to angle AOS by CPCT. Let's call them angle 7 and angle 8. In the same way, angle 1 is equal to angle 2, angle 3 is equal to angle 4, and angle 5 is equal to angle 6. We know that sum of all these angles is 360 degrees. Rearranging gives us, that means twice of angle 2 plus angle 3 plus twice of angle 6 plus angle 7 is equal to 360 degrees. That means angle 2 plus angle 3 plus angle 6 plus angle 7 is equal to 180 degrees. Or we can say angle COD plus angle AOB is equal to 180 degrees. Similarly, it can be proved that angle BOC plus angle DOA is also equal to 180 degree. Therefore, the opposite sides of any quadrilateral which circumscribes a given circle will subtend supplementary angles at the center of the circle. Thank you. With this, we come to an end of this wonderful, wonderful chapter. Hope you liked it. In that case, do hit the like button, subscribe to the channel, and press the bell icon for future updates. So, guys, keep rocking, keep watching I Say Kids, and keep loving us. Have a great day. Bye bye.